2, 1. All right, now we're back. Welcome to part 2 of the ocean circulation lecture and deep water formations. So we know you got some rain happening here at the polar front here, and we have evaporation happening at the subtropical high, and we have sea ice forming in the polar regions. So we're going to look at a couple of these waters. I've also adapted the experiment a little more to sort of put some dry ice in the salt water to speed up the rate of sea ice formation. And we're going to take a look at the actual sea ice itself and what it looks like in a minute or so. First thing I wanted to do was show you just how successful we've been at forming sea ice by taking a look at the bottom of this. All of this is sea ice that formed on the bottom of here when the cold air, or in this case the dry ice, was exposed to the surface of the water. And so the question is the sea ice richer in salt or poorer in salt compared to its the surrounding water? And the short answer is it's likely this ice tends to preferentially select out water and reject the salt in a process known as brine rejection. We're going to see if we can actually see that by carefully, yes, careful is the mode of the word, caution, safety, all these things. Carefully adding a little bit of food dye here. Letting it settle into the ice, perfect. Then gently placing this back on the bottom here. And if we're lucky, we will get a nice plume from the brine rejection. If we're not lucky, that dye will just freeze in place and nothing will happen. We'll also try it here on this one, which hopefully also has a healthy coat of sea ice. Not quite as healthy, but there's still some. Not too bad, actually. Very small drop right here at the surface. Nice, there it is, it's rising. Now put our sea ice formation site right atop it. Carefully. Watch what happens to this. Now here we have some more sea ice forming in this glass here. In fact, we have a bit of frost forming because there's clearly some moisture in the air of the room. And the temperature of the glass is now below the dew point of air for this room. What we're going to do is break this up. We're going to separate out some of these pieces of sea ice that formed here from the dry ice. As you can see, the sea ice formation can create quite a bit of ice and remove quite a bit of material from the water. And we're still getting evaporation in our subtropical high over there. And we do have evaporation on tropical oceans, but there's rainfall outweighs the evaporation, so there's a net input of fresh water in the very low latitudes near the ITCZ. Wow, this is really slushy. And just because we have some slush here, I'm going to have everyone's favorite color to the slush. Yellow, everyone's favorite color for dye. Dyeing water and water-related things. So there we go. Oh, there we go. We got it. Now, meanwhile, we can look back at the polar water, the brine rejection. We can see it very clearly, this beautiful downward plume of deep water formation from just a small pod of the brine rejected water. Ooh, I'm hoping we caught that on the camera, but wow, this is the best that's actually ever come out, so we're doing something right here. So what we see here is just, in the meantime, we've been sort of removing some of the slush and dyeing it the color of snow you probably don't want to go too near in the winter. As the sea ice was forming on the bottom of this little dish that's exposed to cold air, the ice has concentrated the salt water, and we've gotten brine rejected, and what's happened is the remaining water is both cold and salty, extra salty, and that extra saltiness has sent this water to the bottom of the tank in a pretty substantial form. And you can see this process is quite a vigorous one and can move water actually to the bottom of the ocean quite quickly. I'm going to add a couple more drops to this system just because I'm so impressed with how nicely it's operating. Normally it does not work this well. Well, when I try to do this in a classroom, probably because I'm less focused. There we go. All right. Yeah, you can see it really rapidly as the sea ice forms. The brine rejected. The brine, the extra salty water that's rejected as the ice formation preferentially favors the fresh, takes away the fresh water. Do not do what I just did there. Causes the plume, creates this very vigorous plume of salty water going to the bottom. You can really see this, and we'll zoom in on this because we're really starting to see how vigorous. And this happens both in the Arctic and Antarctic, along the any place sea ice is forming. And in fact, this plume of cold, salty water is forms so vigorously in the Antarctic that it actually protects many of the ice streams and ice sheets that drain into the Southern Ocean from being melted by the oceans, by ocean water, because that plume goes downward. Now that we got this vigorous plume, though, of and we call this stuff over here, we call it the Antarctic bottom water, or AABW. And this stuff will, give it a chance, flow all the way down. Antarctic bottom water. Whereas what we're seeing over here, where you have in the North Atlantic, off the coast of Greenland, you're getting North Atlantic deep water. Okay, that has really evaporated pretty nicely. I'm very pleased. I can't wait to see how this will turn out. Call this North Atlantic deep water. This is also what happens to a good bit of the Gulf, some of the Gulf Stream waters as they. So the North Atlantic will be mostly NADW, and then at some point this tongue of North Atlantic deep water will overlap the Antarctic bottom water. The general gist of this is that our deep oceans are quite cold regardless of which basin you are. Now the one place where the deep ocean is not quite as cold is the Mediterranean, which if you look at any map, let's see, we can just turn over to this side of the room here, if that's not going to knock over the camera. Here we have this beautiful, mostly enclosed basin. Not a lot of ice forms here. We do get some sea ice in a very, very cold winter, but for the most part, this is a fairly warm subtropical region that experiences higher rates of evaporation than it does precipitation and river flow. Just like that kettle we had going right here. So what we're going to do is take some of that kettle water, and we'll rinse this bugger out. Watch what happens when we pour some of this. Oh yeah, this will look interesting. Just a quick look. I think we might have gotten a little carried away with this experiment, but we'll see what happens. We left the kettle on for quite a long time. There's actually a sort of slush of ice at the top of this, or not ice, but salt. So here's that warm, salty water. It started out in the ocean. Now we also added a little food dye for dramatic effect. Yeah, you can really see how salty this stuff is. It's in fact losing salt now. It's precipitating out at the bottom. Probably want to, yeah, we're going to want to rinse this. Okay. We've gotten this water about as salty as we can to really concentrate the brine. We're going to create some Mediterranean water, pour it right in very carefully. which one we're doing in. We'll do in this. Let's do it in this one, the northern. Watch what happens when we pour this Mediterranean water. Ooh, yeah. Wow. That brine went straight to the bottom of the ocean because it was much higher in salt. Now one of the questions people often ask is which of these is going to be a more efficient and vigorous formation of deep water, the North Atlantic deep water, or the brine rejection by sea ice formation, or is it this evaporation in the subtropical oceans? This model's not going to give us a very accurate picture of it because we really evaporated the crap out of this water, whereas the sea ice formation, and we added a lot more energy per unit mass of water than is physically possible for the subtropical oceans in the Mediterranean. Whereas the sea ice formation, we can't quite increase the rate of things quite as dramatically. So you can already see in this case the super deep Mediterranean water is actually creeping in underneath the brine rejected North Atlantic deep water. But if this were an actual ocean, your subtropical salty intermediate water would sort of kind of form would be right about here. However, during the Cretaceous and other ice-free periods, this sort of warm, salty water was much more prevalent, and this was how we got a deep water formation, because we did not have sea ice formation, and we had much warmer oceans. So this process of what we're seeing here is known as halothermal circulation, where evaporation drives the formation of deep water, whereas over in these two basins are seeing thermohaline circulation, where very cold temperatures and sea ice formation drive the formation of deep water. Now we're going to do one more experiment as part of part 3 here. And so first we're going to, just for more dramatic effect, clear out more of this brine. Clear out more of this brine-rejected sea ice, and that's leaving behind a brine. Actually, I think we're going to pause for now. We'll come back for part 3.